Our universe is built on a foundation of rules we barely understand. Hidden within the cosmos are 22 cosmic anomalies that defy explanation, from the relentless push of dark energy to galaxies spinning too fast for their own good. By the end of this journey, you will see how these puzzles could completely rewrite the laws of physics. We will uncover why stars vanish in erratic blinks of light, and what mysterious force might be tugging at our entire galaxy. What one cosmic mystery keeps you up at night, wondering what else is out there? Everything we thought we knew about the cosmos changed in 1998. Astronomers made a discovery so shocking it ripped a hole in our understanding of the universe. They found that the universe is not just expanding, it is accelerating. Galaxies are flying apart from each other at a faster and faster rate. This was the complete opposite of what everyone expected. Gravity, the force that pulls everything together, should be putting the brakes on this expansion, slowing it down over billions of years. Instead, something is stepping on the cosmic gas pedal. That something is what we call dark energy. It is the name we give to our ignorance, a placeholder for a mysterious force that seems to be woven into the very fabric of empty space, pushing it apart. This discovery was so profound it earned the Nobel Prize in Physics for the teams led by Saul Perlmutter and others. They were not looking for this. They were measuring distant stellar explosions called Type 1, a supernova, using them as cosmic mile markers to gauge the expansion history. The light from these supernovae was fainter than it should have been, meaning they were farther away than expected. The only explanation was that the expansion of the universe had sped up in the distant past, pushing these galaxies even farther from us. Later, data from the cosmic microwave background, the faint afterglow of the Big Bang, confirmed this bizarre reality. Dark energy is not a small effect. It makes up about 68% of everything in the universe. It is the dominant force shaping our cosmic destiny. This single anomaly shatters the standard model of physics. If dark energy is Einstein's cosmological constant, an energy inherent to space itself, its observed strength is a number so impossibly small and fine-tuned that it seems like a bizarre cosmic coincidence. But what if it is not constant? What if this repulsive force evolves over time or interacts with matter in ways we have not yet detected? Such a possibility would force us to rewrite Einstein's theory of general relativity itself, leading us toward a new theory of gravity. The ultimate fate of the cosmos, whether it ends in a cold, lonely tear or a catastrophic rip, hinges on the true nature of this phantom. And just as we grapple with this invisible force pushing the universe apart, we must confront another mystery, one that hints at a force pulling our own galaxy in a direction we cannot explain. This ghostly gravitational pull is not confined to the vast emptiness between galaxies. It leaves its fingerprints on the galaxies themselves, in a phenomenon so strange it forced astronomers to invent an entirely new form of matter. Take a majestic spiral galaxy like our own Milky Way. According to the well-tested laws of gravity laid down by Isaac Newton, stars orbiting the galactic center should behave like planets in our solar system. Those closer to the Sun orbit blisteringly fast, while distant Pluto plods along at a relative crawl. The same logic should apply to a galaxy. The stars near the bright, crowded center, where most of the visible mass is concentrated, should whip around at high speeds. Meanwhile, stars out in the sparse, dark edges of the galactic disk should be moving much more slowly, feeling a weaker gravitational tug from the core. But they do not. When astronomer Vera Rubin meticulously measured the rotation speeds of stars in the Andromeda galaxy, she found something that defied this simple prediction. Stars at the very edge of the galaxy were orbiting just as fast as those near the center. It was as if every car on a highway, regardless of whether it was near a city or out in the open countryside, was traveling at exactly the same speed. The only way this makes any sense is if the galaxy is embedded within a massive, invisible halo of something that provides extra gravity to keep those outer stars from flying off into the void. We call this something dark matter. This is not just a small adjustment. The math is brutally clear. For the rotation curves of galaxies to be so flat, there must be about 5 times more of this dark matter than there is normal, visible matter. It makes up roughly 27% of the universe. It is the cosmic scaffolding upon which galaxies are built. We see its effects everywhere we look. When two giant clusters of galaxies collide, we can watch the separation of dark matter from everything else. Observations of one such collision, known as the bullet cluster, show that most of the mass mapped through gravitational lensing clearly passes right through the collision, while the clouds of hot gas, the normal matter, slam into each other and slow down. The dark matter just keeps going, barely interacting at all. So what is it made of? For decades, the leading candidates have been particles known as WIMP, or weakly interacting massive particles. These are hypothetical heavy particles that barely talk to normal matter, only making their presence known through gravity. Another compelling idea involves particles called actions, which are trillions of times lighter but could also account for the missing mass. After decades of searches deep underground in ultra-sensitive detectors, we have not found a definitive signal for either. The true identity of dark matter remains one of the greatest puzzles in all of science. Solving it would do more than just check a box in astronomy. It would open a portal into a hidden sector of the universe, revealing new fundamental particles and forces that have shaped cosmic history from the very beginning. And just as this unseen matter dictates the fate of galaxies, other, stranger gravitational phenomena are warping the very fabric of reality itself. Two of the most trusted methods for measuring the universe's expansion rate are now telling us two different stories. This growing rift, known as the Hubble Tension, is a crack in the very foundation of modern cosmology. On one side, we have the view of the early universe, meticulously mapped by the Planck satellite. It observed the cosmic microwave background, the faint afterglow of the Big Bang, and used our well-established model of the cosmos to predict how fast the universe should be expanding today. On the other side, we have observations from powerful telescopes like Hubble, which look at stars and supernova in our local, modern universe to directly measure that expansion rate. The two numbers should agree perfectly, but they do not. The local universe appears to be expanding significantly faster than the early universe data predicts. This is not a small, insignificant error. The discrepancy has a high statistical significance, meaning it is very unlikely to be a simple fluke. It has persisted and even grown as measurements have become more and more refined in recent surveys. Cosmologists are now forced to ask a profound question. Is there a flaw in our standard model of the universe, a model that has been incredibly successful for decades? Some theorists suggest the existence of early dark energy, a temporary, exotic form of energy that might have briefly surged in the universe's first moments, altering its initial conditions just enough to explain the mismatch. Others wonder if we need to modify our understanding of gravity itself on the largest scales. What does this conflict mean for the age and fate of the cosmos? If the local measurement is correct, the universe might be a bit younger than we thought. More importantly, it hints that there were unknown forces or particles at play during the universe's infancy, elements that are missing from our current cosmic story. This direct challenge to our most fundamental model forces us to look even closer at that ancient afterglow, the cosmic microwave background, where other, stranger anomalies are hiding in plain sight. This faint afterglow of creation is not perfectly smooth. It is a tapestry of minute temperature variations, a snapshot of the universe when it was just 380,000 years old. Most of these fluctuations are tiny, but one region stands out as profoundly strange. Stretching across a vast swath of the southern sky is a colossal cold spot, a patch of the cosmic microwave background that is significantly colder than its surroundings. This is not just a statistical blip. It is so large and so cold that it challenges our understanding of how the universe evolved. Think of the early universe as a calm pond after a heavy rain. The surface is covered in ripples, small waves representing the density variations that would one day grow into galaxies. The cold spot is like a single, enormous, and unexpected trough in that pond, a depression so deep and wide it does not quite fit with the rest of the pattern. Standard cosmic inflation, the theory of the universe's rapid initial expansion, struggles to explain how such a gigantic feature could have formed naturally. So what could have caused it? Some scientists propose it might be the imprint of a cosmic defect, a relic from a phase transition in the primordial universe, like a crack frozen into the fabric of spacetime. An even more mind-bending possibility comes from theoretical work by physicists like Laura Mersini-Horton. She suggests the cold spot could be a bruise, evidence of a collision between our universe and another bubble universe in the vast multiverse. In this scenario, the energy of that long-ago impact would have drained away, leaving behind a cold, empty scar on our sky. While this idea is speculative, it highlights how seriously cosmologists are taking this anomaly. Could this cold patch be a window into physics from before the Big Bang, or a sign of forces we have not yet discovered? Its very existence whispers that our universe might not be as uniform as we once believed, pushing us to look for other primordial fingerprints. And if we listen closely to the echoes of creation, we might even hear the faint tremors of another early universe mystery, one written in the language of gravitational waves. Long before the first stars ignited, the infant universe was a turbulent sea of spacetime itself. In its first fleeting moments, a theorized period of hyper-expansion called inflation is thought to have stretched the very fabric of reality, generating ripples that would echo for billions of years. These are primordial gravitational waves, the faintest possible tremors from the dawn of time. Unlike the gravitational waves we have detected from colliding black holes, which are like the loud, sudden crashes of cymbals in a cosmic symphony, primordial waves are the deep, pervasive hum of the orchestra warming up before the music even began. Detecting them would be like finding a fossil from the universe's first trillionth of a second. This is why experts like Kip Thorne see them as the ultimate probe into the Planck epoch, a realm where gravity and quantum mechanics violently clash. To find them, scientists turn to the oldest light we can see, the cosmic microwave background. As this ancient light traveled through the infant cosmos, the squeeze and stretch of these primordial ripples would have left a distinct twisted pattern, a specific type of polarization known as B modes imprinted upon it. Experiments like BICEP, located at the South Pole to take advantage of the ultra-dry, stable air, scan this afterglow with incredible precision, hunting for that faint, curling signature. The challenge is monumental. This signal is incredibly weak, easily mimicked by the swirling dust of our own galaxy or other foreground effects. A claimed detection in 2014 was later shown to be largely due to this interstellar dust, a sobering reminder of how difficult this search truly is. Yet the potential reward is a complete rewriting of physics. A clear detection would not only confirm the theory of cosmic inflation, but would tell us the energy scale at which it happened. a direct window into the ferocious power of the Big Bang. It could provide the first experimental evidence for string theory or even the multiverse, ideas that currently reside in the realm of pure mathematics. But what if we never find them? Their continued absence would be just as profound, forcing us to consider alternative models of the universe's birth where such waves were never produced, or where new, unknown dynamics were at play. This search for the universe's first vibrations pushes our technology to the absolute limit, all to listen for a whisper that has been fading for over 13 billion years. And if the fabric of spacetime itself holds such deep secrets, then the grand structures built upon it must hold clues of their own. Our galaxy is caught in a silent, relentless river of motion. The Milky Way is not simply drifting aimlessly through the cosmos. It is being pulled, along with our entire local group of galaxies, toward a specific point in space, a mysterious gravitational anchor we call the Great Attractor. This region, located in the direction of the constellation Centaurus, exerts a powerful pull, but its core is hidden from our direct view, obscured by the dense plane of our own galaxy's dust and stars. For a long time, its true nature was a profound puzzle. Then, astronomers realized the motion was even more complex. We are not just being pulled toward something. We are also being pushed away from an immense cosmic void, an underdense region of space so vast and empty it acts as a repeller. This is the Dipole repeller, a place where the scarcity of galaxies creates a kind of negative gravity, shunting matter away. Think of it like a ball rolling down a hill. The Great Attractor is the deep valley at the bottom, pulling the ball downward. But the dipole repeller is the high plateau behind you, giving you an extra shove forward. Our galaxy is caught between this push and this pull. To map these immense flows, scientists study the peculiar velocities of galaxies. This involves comparing a galaxy's motion due to the overall expansion of the universe with its own unique, local motion caused by the gravitational tug of its neighbors. It is like watching leaves floating down a river. Some leaves drift with the current, but others are caught in eddies and whirlpools, moving in unexpected directions. By conducting massive redshift surveys that map the three-dimensional positions and motions of millions of galaxies, we can trace these cosmic currents. The result is a breathtaking new understanding of our cosmic address. We now see that our Milky Way is part of the Laniakea supercluster, a web of 100,000 galaxies all flowing toward the same gravitational basin, the Great Attractor. But the sheer scale of this motion presents a problem. The amount of visible mass in the Great Attractor region does not seem sufficient to generate such a powerful pull. Once again, dark matter provides a compelling explanation. Perhaps the Great Attractor is not a single, dense cluster, but the focal point of an enormous, invisible concentration of dark matter, a knot in the cosmic web whose gravity dictates the flow of an entire supercluster. Alternatively, the profound emptiness of the dipole repeller might be the real key. Voids are not passive, empty space. In an expanding universe, an underdense region effectively exerts a repulsive force, pushing galaxies toward the denser filaments and nodes. This cosmic tug-of-war between the pull of hidden mass and the push of profound emptiness shapes the largest structures we can observe. Could these immense flows be telling us that gravity itself behaves differently on scales larger than a supercluster? Or do they simply reveal the true, hidden architecture of the dark matter cosmos? An architecture whose next level of complexity is written in the very shape of the galaxies themselves. Galaxies are not always the bright, dense whirlpools of stars we typically imagine. Drifting through the darkness of space are cosmic ghosts, objects so faint and ethereal they barely register against the blackness of the void. These are ultra-diffuse galaxies, and they defy everything we thought we knew about how galaxies form and survive. Take Dragonfly 44, a galaxy located in the Coma cluster. From our perspective, it is as large as our own Milky Way, but it contains only 1% of the stars. It is a vast, wispy cloud of a galaxy, a skeleton with almost no flesh. You could look right through it and barely know it was there. Yet, when astronomers measured the motions of its few visible star clusters, they found they were whipping around at astonishing speeds. The gravity required to hold these stars in orbit, preventing them from flying off into intergalactic space, is immense. This ghostly galaxy behaves as if it is dominated by a colossal, invisible halo of dark matter. How can something so empty be so heavy? The existence of these wispy giants poses a severe challenge. How do they not just tear themselves apart? And more puzzlingly, how do they survive in hostile environments like the heart of a dense galaxy cluster? These regions are cosmic demolition derbies, filled with violent gravitational tides and scorching hot plasma that should shred a fragile, low-density galaxy to pieces. Yet, observations from the Hubble Space Telescope and the Keck Observatory reveal that many ultra-diffuse galaxies in the Coma cluster are not being destroyed. They are stable, enduring objects. This unexpected stability points to a hidden strength. Their dark matter halos must be extraordinarily dense and tightly packed, acting as an invisible shield that protects their delicate stellar populations from the cluster's harsh forces. So how did these cosmic paradoxes come to be? One leading theory suggests they are failed galaxies. Early in the universe, a cloud of dark matter may have begun to collapse, but for some reason, the process of gas accretion and star formation was stunted, leaving behind a dark matter-dominated relic with only a sparse sprinkling of stars. Another idea is that they are the products of violent tidal interactions where larger galaxies ripped stars away from one another, leaving behind these stretched, ghostly remnants. Each ultra-diffuse galaxy is a natural laboratory, testing our models of how dark matter and normal matter interact on the smallest cosmic scales. If their dark matter is distributed differently than in normal galaxies, it could mean our understanding of dark matter particle physics is incomplete. Could these faint, wispy ghosts be the key to unlocking the true nature of the universe's most elusive ingredient? Their silent endurance forces us to look for dark matter's signature in even more extreme and isolated environments. Out in the depths of space, a cosmic strobe light flashes with unimaginable power. These are fast radio bursts, colossal blasts of radio waves that last for just a few thousandths of a second. Yet in that fleeting instant, they can release more energy than our sun does over 3 entire days. The first of these bursts was discovered by astronomer Duncan Lorimer in 2007, buried in archived data from a radio telescope, and it seemed so bizarre that some wondered if it was merely an instrument glitch. But then more were found, confirming we were witnessing a real and profoundly violent cosmic phenomenon. The mystery only deepened when we realized these bursts come in 2 distinct flavors. Some are one-off events, a single, tremendous crackle from the void, but others, like the famous FRB 1211-2, repeat erratically, firing off multiple bursts from the same patch of sky. This tells us that whatever is causing them cannot be a cataclysm that destroys the source, at least not for the repeaters. So what cosmic engine can switch on and off so violently and so quickly? The list of suspects is as exotic as the bursts themselves. Highly magnetized neutron stars called magnetars are a prime candidate, capable of producing starquakes or explosive magnetic flares that could generate such a signal. Others might be born from the final, furious merger of 2 neutron stars. but the sheer diversity of the burst suggests we might be looking at multiple different sources, perhaps even some that involve entirely new physics. The journey of these radio waves across the universe is just as revealing as their origin. As an FRB travels through the sparse sea of electrons that fills the space between galaxies, higher frequency waves arrive at our telescopes just a fraction of a second before the lower frequencies. This effect, called dispersion, acts like a cosmic odometer. By measuring the stretch in the signal, astronomers can calculate the total amount of material the burst has traveled through, allowing us to literally weigh the missing ordinary matter in the cosmic web. Some bursts even exhibit a curious twisting, a phenomenon known as Faraday rotation, which reveals the strength of the magnetic fields they have passed through. FRB 1211-2 was a landmark, the first burst we managed to pin down to a specific home. It originated in a small, turbulent dwarf galaxy over 3 billion light-years away, an environment perfect for forming the kind of young, volatile magnetars that could be responsible. Yet for every clue, a new question arises. Why do some sources go silent for years only to suddenly reactivate? Could the most extreme, one-off bursts be evidence of something even more fantastic, like the evaporation of a primordial black hole or the vibrations of cosmic strings? While it is a remote possibility, some have even speculated whether a technologically advanced civilization could be capable of generating such powerful, focused signals, perhaps to push light sails across interstellar distances. The search for answers is driving a new era of radio astronomy, with dedicated telescopes like CHIME in Canada scanning the entire sky every day, catching dozens of these enigmatic flashes. Each one is a message in a bottle hurled across billions of light-years, carrying with it the signature of every particle and field it has ever touched. If fast radio bursts are the universe's most powerful and fleeting radio shouts, then the cosmos also sends us messengers of a different kind, silent, massive particles that arrive with the punch of a well-thrown baseball. A well-thrown baseball carries a tiny amount of energy, but out in the deepest voids of space, there are atomic nuclei traveling with the punch of a professional fastball. These are ultra-high-energy cosmic rays, the most energetic particles ever observed in nature. A single one can carry the energy of a falling brick, all compressed into a subatomic speck smaller than an atom. We are talking about energies millions of times more powerful than anything achievable in our greatest particle colliders, like the Large Hadron Collider. The record holder, nicknamed the Oh My God particle detected in 1991, was so energetic that it defied belief, moving at a velocity so close to the speed of light that from its perspective, the entire galaxy would have been compressed into a thin pancake. According to our current understanding of physics, such particles should not be able to travel very far at all. There is a theoretical limit called the GZK Cutoff, named for physicists Gryzin, Zatsepin, and Kuzmin. It states that particles with this much energy should be constantly bumping into the photons of the cosmic microwave background, the leftover heat from the Big Bang. These collisions would sap their energy over distances of a few 100 million light-years, like a marathon runner constantly tripping over tiny pebbles. The existence of the Oh My God particle and others like it means they either come from very nearby sources in our cosmic neighborhood, or our understanding of how particles interact at these extreme energies is fundamentally wrong. So where do they come from? To hunt for their origins, physicists built colossal observatories like the Pierre Auger Observatory in Argentina, which uses thousands of water tanks spread over an area the size of Rhode Island to detect the cascading shower of secondary particles created when a cosmic ray slams into our atmosphere. The results have been deeply puzzling. When they trace the incoming paths of these ultra-high-energy particles back to their source, They often point to seemingly empty patches of sky, vast cosmic voids where no violent galaxies or brilliant quasars are seen. It is as if a sniper is firing from an empty room. This forces us to consider some extraordinary possibilities. Perhaps the engines are active galactic nuclei, the supermassive black holes at the centers of galaxies, which can whip particles to these speeds in their immense magnetic fields. Or maybe the source is a gamma-ray burst, the most powerful explosion since the Big Bang itself, acting as a temporary cosmic cannon. An even more exotic theory points to the decay of super-heavy dark matter. This idea proposes that in the early universe, a population of incredibly massive particles was created, and they have been silently decaying ever since, occasionally spitting out a particle with unimaginable energy. If this is true, then detecting these cosmic rays is our first direct glimpse into the particle nature of dark matter. Solving this mystery would do more than just identify a celestial particle accelerator. It would open a window into particle physics at energy scales we can never hope to build on Earth, potentially revealing new fundamental forces or dimensions. Each of these rare, powerful particles is a messenger hurled across the universe by a phenomenon we do not yet comprehend. And if the cosmos can accelerate single particles to such impossible speeds, what other energetic secrets are hiding within the violent lives and deaths of stars themselves? A star over 1,000 light-years away performs a light show that defies all logic. KIC 8462852, known as Boyajian star, flickers and dims in a way no other star we have ever seen does. Its light does not dip in the predictable, rhythmic pattern of an orbiting planet. Instead, it plunges by staggering amounts, up to 22%, in chaotic, asymmetrical drops that can last for days before brightening again. When the Kepler Space Telescope first captured this bizarre behavior, astronomers were stunned. Planets, even giant ones, block only about 1% of a star's light. Something enormous and strangely shaped was passing in front of this star. The initial theories were as wild as the data. Could it be a vast, fragmented planet, the debris from a catastrophic collision? Or was it an immense swarm of comets, thousands of them, on a long, eccentric orbit around the star? The most speculative idea, popularized by astronomer Jason Wright, was that we might be witnessing a Dyson swarm under construction, a colossal array of energy-collecting structures built by an advanced civilization. The star's namesake, Tabetha Boyajian, championed a more natural explanation focusing on circumstellar dust. This dust would be irregular and fine, explaining both the deep, irregular dips and why the star appears redder when it dims, as dust scatters blue light more effectively. Yet, even this compelling explanation runs into problems. Long-term studies revealed another layer to the mystery. Not only does the star drop in brightness erratically, but it has also been undergoing a steady, long-term dimming over the course of the last century, as found in archival data from old photographic plates. This combination of sudden, deep eclipses and a century-long fade is a puzzle with no single, satisfying solution. Every new observation seems to deepen the enigma. Follow-up studies with the Los Cumbres Observatory Global Telescope Network have caught the star dipping at unexpected times, confirming the irregularity. What natural process could possibly account for such dramatic and random obscuration? The answer may lie in a phenomenon we have never before observed, perhaps the aftermath of a planetary collision that left a massive, evolving cloud of debris, or a new type of stellar activity that generates immense clouds of opaque material. Boyajian's star is a masterclass in scientific humility, reminding us that our catalogue of cosmic phenomena is far from complete. It forces us to question our assumptions about what is normal in a star system and sharpens our methods for finding other worlds. If we cannot explain the light from this one star, what other strange signatures are we overlooking in the data? This stellar mystery pushes us to consider the possibility of entirely new astrophysical processes, a theme that echoes in the violent demise of stars elsewhere in the cosmos. Rising from the heart of our galaxy like two colossal, ghostly orbs are structures that defy our quiet picture of the Milky Way. These are the Fermi Bubbles, vast balloons of superheated gas and high-energy radiation that stretch for 25,000 light-years above and below the galactic plane. They are completely invisible to the human eye, glowing only in the most energetic light, gamma rays. It was NASA's Fermi Gamma Ray Space Telescope that first revealed their full extent, showing us that our galactic home is not as peaceful as it seems. These bubbles are the remnants of a cataclysm, a titanic explosion that erupted from the center of the Milky Way sometime in the past. But what could have unleashed such fury? The prime suspect is our own supermassive black hole, Sagittarius A star. While it is quiet today, it may have been a brilliant active galactic nucleus in the past, feasting on a massive influx of gas and stars. This feeding frenzy would have generated powerful jets and an immense wind, blowing these gigantic bubbles out into intergalactic space. Another possibility points to a frenzy of star formation in the galactic center, where the collective winds from millions of newborn stars and their subsequent supernova explosions could have combined to create the same colossal structures. The key to distinguishing between these two cosmic engines lies in the detailed spectrum of the gamma rays and the precise shape of the bubbles themselves. Are the edges razor-sharp, suggesting a rapid, violent outburst from the black hole, or are they more diffuse, hinting at a slower, more sustained wind from stellar processes? Multi-wavelength observations have added crucial pieces to the puzzle. The E-Rosetta telescope has seen giant X-ray bubbles that align almost perfectly with the Fermi structures, suggesting they are different facets of the same enormous event. Meanwhile, radio telescopes have mapped mysterious parallel structures nicknamed the Fermi Bubbles cousins, further complicating the story. This tells us the event was not a simple blast, but a complex, multi-stage feedback process where energy was injected, transferred, and dissipated across different forms. Could these bubbles be the key to understanding the cyclical nature of galactic black holes? They suggest that even our own seemingly dormant giant can awaken in violent, transformative episodes that reshape the entire galaxy, heating the surrounding gas and potentially shutting down star formation for eons. The silent, invisible bubbles hovering over us are a permanent monument to a forgotten age of violence, forcing us to ask what other dormant giants in nearby galaxies might be hiding similar explosive histories. The violence of stellar death typically leaves behind two types of relics. On one end are stellar mass black holes, the remains of massive stars weighing up to a few dozen times the mass of our Sun. On the other are the supermassive black holes, monsters millions or even billions of times heavier than the Sun, which lurk in the hearts of galaxies. For decades, a profound gap existed between them, a vast desert in the black hole mass spectrum. Where were the intermediate mass black holes, these elusive objects with masses ranging from a few hundred to a few 100,000 solar masses, represent a crucial missing link in cosmic evolution. Their very existence challenges our models of how black holes grow from modest seeds into the galactic behemoths we observe today. How does a universe that creates stellar mass black holes skip directly to the supermassive variety without any intermediate steps? Finding them has been a monumental task, as they do not announce their presence as brightly as their larger cousins. One of the most promising hunting grounds is within the ancient, dense clusters of stars known as globular clusters. In these stellar swarms, where stars are packed 1,000 times tighter than in our galactic neighborhood, dynamic chaos can reign. Experts like Professor Holger Baumgart use sophisticated computer simulations to model these environments. They explore the possibility of runaway stellar collisions, where stars merge repeatedly over eons, building up a massive object that eventually collapses directly into an intermediate mass black hole. Another, more exotic idea is that they are primordial, forming not from stars but from the direct collapse of immense density fluctuations in the universe's first moments. The evidence for these hidden giants is often indirect but compelling. Astronomers search for the telltale X-ray glow of a hot accretion disk, formed as the black hole slowly pulls material from a companion star in an X-ray binary. They also look for the spectacular flare of a tidal disruption event, the signature of a star being ripped apart by the black hole's immense gravity. One of the best candidates is an object known as HLX-1, or hyperluminous X-ray source 1, in a distant galaxy. It shines with the power of millions of suns in X-rays, far too bright to be a stellar mass black hole, yet it resides far from the galactic center, ruling out a supermassive one. Yet, confirming its nature is incredibly difficult. The signals are faint, the events are rare, and alternative explanations, like a cluster of stellar mass black holes, are always possible. Each new gravitational wave detection from merging black holes by observatories like LIGO and Virgo also offers a potential clue. The components of some mergers appear to fall squarely into this intermediate mass range, suggesting these objects are out there, colliding in the dark. If they are real, intermediate mass black holes could be the long-sought seeds from which all supermassive black holes grow. They are the potential missing chapter in the story of cosmic structure, the hidden anchors that dictated the formation of the first galaxies. Their confirmed discovery would force us to rewrite the book on black hole growth, revealing a universe where the paths to cosmic power are far more varied and violent than we ever dreamed. And if the fabric of space-time can be tied into such elusive knots, what other wrinkles in reality might be hiding just beyond our perception? Even the most precisely engineered journeys can carry a hidden, unplanned drag. For the Pioneer 10 and 11 spacecraft, humanity's first emissaries to the outer planets, this drag manifested as a ghostly whisper of a force. As they sailed beyond Jupiter and Saturn into the dark, their trajectories were tracked with exquisite care by NASA, a deep space network. The data revealed something deeply puzzling. Both spacecraft were experiencing a constant, tiny, sunward deceleration, a slowdown so minute it was equivalent to just 1/10,000,000th of the gravity we feel on Earth. Yet over years and billions of miles, this minuscule anomaly added up, pulling the Pioneers hundreds of kilometers off their predicted courses. This was the Pioneer Anomaly, a stubborn deviation that defied immediate explanation for decades. It was a riddle written in the language of orbital mechanics, a signal so faint it flirted with the very limits of measurement. The implications, however, were anything but small. Could this be the first hint of a modification to Newton's law of gravity at extremely weak accelerations, a theory known as modified Newtonian dynamics, or MND? Or was it evidence of some unknown particle streaming from the Sun, providing a gentle cosmic break? The search for an answer became a masterclass in forensic engineering. Teams of scientists meticulously modeled every conceivable force acting on the aging probes. They accounted for the gentle push of the solar wind, the gravitational tug of distant Kuiper belt objects, and even the minuscule pressure from the spacecraft's own radio signals. The breakthrough came when they turned their attention inward to the spacecraft themselves. Pioneer's electrical systems and radioactive power source generated heat, which was radiated away into space. Through sophisticated thermal modeling, engineers realized that this heat did not radiate perfectly symmetrically. a tiny, anisotropic fraction of this thermal radiation was preferentially emitted from the back of the spacecraft's main antenna dish. This created a recoil effect, a photon rocket on a microscopic scale, providing just enough continuous thrust in the wrong direction to explain the observed deceleration. The ghost was largely a thermal one, yet for some, a sliver of the anomaly remains unaccounted for, a reminder that our models are never perfectly complete. This case echoes in modern missions. The New Horizons probe, now speeding through the Kuiper belt, is tracked with even greater precision, its trajectory scrutinized for any similar deviation. The lesson of Pioneer is profound. It teaches us that before we invoke new physics to explain the cosmos, we must first become masters of our own creation, understanding how a trickle of heat or a whisper of gas can mimic the pull of an unseen force. It is a cautionary tale that grounds our grandest theories in the gritty reality of engineering. And if a spacecraft's own warmth can create such a convincing cosmic mystery, what other subtle forces might be at play, not in the void of space, but within the familiar orbits of our own solar system? 14 times we have swung a spacecraft past our own planet, using its gravity as a cosmic slingshot to hurl probes toward distant worlds. Yet on several of these occasions, something in the math has gone subtly wrong. During these Earth flybys, spacecraft like Galileo and Rosetta have experienced a tiny, unexpected change in speed. They either gained a few millimeters per second more than predicted, or lost it, as if an unseen hand gave them an extra, gentle push or an invisible drag pulled them back. This is the Flyby anomaly, a whisper of a discrepancy that has echoed through multiple missions. The effect is measured through the Doppler shift in the radio signals sent back to Earth. As a spacecraft approaches, its signals are compressed, and as it recedes, they are stretched. By tracking this shift with exquisite precision, engineers can calculate the probe's velocity down to minuscule fractions of a meter per second. It was in this pristine data that the anomaly appeared, a small but persistent deviation from the expected speed. The pattern is strangely linked to the geometry of the flyby itself. The effect seems stronger when the spacecraft's incoming and outgoing trajectories are asymmetrical relative to Earth's equator, and it appears to vary with our planet's rotation. This has led to some profound hypotheses. Could the spinning Earth be dragging the fabric of spacetime around with it more than our models predict, an effect known as frame dragging, imparting an extra kick? Or is the spacecraft briefly plowing through a thin, undetected halo of dark matter gravitationally bound to our planet? The scientific response has been a meticulous process of elimination. Could atmospheric drag be responsible? At the altitudes of these flybys, the atmosphere is a near-perfect vacuum, far too thin to account for the effect. What about the pressure of solar radiation or the heat radiation from the spacecraft itself? As with the Pioneer Anomaly, detailed modeling has shown these contribute, but not nearly enough. Even subtle relativistic corrections have been factored in, yet the discrepancy remains. The Rosetta spacecraft's flyby in 2009 is a perfect case study. Its velocity was tracked with phenomenal accuracy, and it displayed the anomaly clearly, a deviation that standard gravity could not explain. This persistence across different spacecraft and different flyby geometries tells us this is not a simple instrument error. It is a real, physical effect that we are not yet accounting for. Each unexplained millimeter per second is a question mark hovering over our understanding of gravity and motion in Earth's vicinity. Do we need to refine our models of Earth's own gravitational field to an even more incredible degree of precision? Or does this faint signal point toward something entirely new? A novel planetary effect or a hint of physics beyond Einstein? These tiny velocity ticks are a reminder that even in our own celestial backyard, the universe still holds onto a few of its secrets. Far beyond the orbit of Neptune, our solar system does not simply fade into an empty, dark frontier. Instead, it is ringed by the Kuiper belt, a vast disk of icy worlds left over from the dawn of planetary formation. For decades, our models predicted this population of frozen objects would thin out gradually, a gentle cosmic fade as you moved farther from the Sun. But that is not what we see. Surveys, including those from the New Horizons mission after its Pluto flyby, have revealed a startling feature. There is a cliff, a sudden and dramatic drop in the number of Kuiper belt objects beyond a distance of about 50 astronomical units. It is as if a cosmic gardener came through and neatly trimmed the edge of this frozen reservoir. This Kuiper belt cliff defies all expectations of a smooth, natural decline. The sheer abruptness of this boundary suggests something, or someone, has been sculpting the outer solar system. The most tantalizing explanation is the gravitational hand of an unseen planet. This hypothetical world, often called Planet 9, would be a super-Earth lurking hundreds of times farther from the Sun than we are. Its immense gravity, over billions of years, could have shepherded these distant objects, clearing out a vast region and creating this sharp edge we observe today. The orbits of extreme objects like Sedna provide a compelling clue. Sedna follows a long, looping path that never brings it close to the giant planets, as if it was kicked onto this lonely trajectory by a powerful, persistent gravitational influence. Planetary scientists run complex simulations to see if they can recreate this cliff and the strange orbits of these detached objects. The challenge is that any planet massive enough to create these effects would also be incredibly difficult to spot, a dark needle in the cosmic haystack of the outer solar system. An alternative, equally dramatic theory points to a stellar flyby. In the solar system's youth, a passing star could have gravitationally plowed through the primordial Kuiper belt, stripping away the outer population and leaving behind this stark boundary. Each of these scenarios rewrites the history of our cosmic neighborhood. Was our Sun once part of a tighter stellar cluster where such close encounters were common? Or does a true planetary mass object, a world larger than Earth, still wander unseen in the perpetual twilight beyond our current vision? This anomaly forces us to look inward, to question the stability of the very laws that govern our reality. If the outer solar system holds such profound secrets about its formation, what does it say about the fundamental constants that allowed it to form in the first place? Our universe's first few minutes were a frantic nuclear forge. In that searing heat, the very first atomic nuclei were born, a process we call Big Bang nucleosynthesis. Our models of this cosmic alchemy are spectacularly successful, predicting the amounts of hydrogen and helium we see across the cosmos with stunning accuracy. But there is one stubborn ingredient that refuses to fit the recipe: lithium. The light metal lithium exists in two main stable forms, lithium-6 and lithium-7. According to our most trusted calculations, the Big Bang should have produced a specific, small abundance of lithium-7. Yet when we look at the oldest stars in our galaxy, which formed from nearly pristine primordial gas, we find only about 1/3 of the predicted amount. This is not a small measurement error. It is a factor of 3 discrepancy that has resisted explanation for decades, a clear signal that something in our story of the universe's birth is either incomplete or fundamentally wrong. How could our models get hydrogen and helium so perfectly right and lithium so dramatically wrong? Scientists have pursued 2 main paths to solve this puzzle. The first looks to destroy the extra lithium. Could ancient stars themselves be the culprits, somehow processing and depleting this fragile element over billions of years? As these stars churn, lithium, which burns at a relatively low temperature, could be destroyed in their interiors. But getting this depletion to work across all the oldest stars we observe without affecting other elements is a complex and challenging problem. The second path involves cosmic rays. High-energy particles zipping through space can smash into heavier nuclei, fragmenting them and creating new lithium, a process that might have added to the galactic supply after the Big Bang and confused our measurements. Yet, even accounting for this, the primordial deficit remains. This forces physicists to consider far more radical ideas. What if the nuclear reaction rates that occurred in that first fiery furnace were different than we think? A slight change in the probability of certain particles fusing could resolve the mismatch, but it would require new, unknown nuclear physics. An even more profound possibility is that the fundamental constants of nature, like the strength of the forces that bind atomic nuclei, were not quite constant in the universe's first moments. A tiny variation could have thrown off the delicate balance that produced lithium. This single anomaly in the abundance of a light element is a direct challenge to the standard model of particle physics. It hints that there were particles or forces at play in the early universe that we have not yet accounted for, perhaps exotic relics that decayed and altered the nuclear soup. Solving the lithium problem would do more than just fix a number in a textbook. It would give us a clear window into physics at energies far beyond what any particle collider on Earth can reach, revealing secrets from the universe's very first nuclear heartbeat. The cosmic blueprint of the universe seems to have a strange, unexpected wrinkle. When we look at the oldest light in the cosmos, the cosmic microwave background, we expect to see a random splatter of hot and cold spots, a pattern with no preferred direction, confirming the universe is fundamentally the same everywhere. This is the cosmological principle, a cornerstone of modern science. But the data from the Planck satellite reveals something unsettling. The largest fluctuations in this ancient radiation appear to be subtly aligned with the plane of our own solar system. Scientists have nicknamed this correlation the axis of evil, not for any malevolent quality, but because it so deeply violates our expectations of cosmic indifference. How could the grandest features of the entire universe possibly know about the insignificant tilt of our little planetary disk? The analysis hinges on something called multiple moments, a mathematical way of describing the pattern of hot and cold spots across the sky. The dipole is the simplest, showing the overall hot and cold hemispheres caused by our motion through space. The quadrupole and octupole describe more complex, larger-scale patterns. It is in these larger patterns that the strange alignment appears, as if the universe's most fundamental imprints are whispering a secret connected to our own backyard. The probability of this happening by pure chance is incredibly low, forcing cosmologists to confront two equally profound possibilities. The first is that we are seeing a statistical fluke of monumental proportions, a 1 in 1,000 cosmic coincidence that just happens to manifest in our all-sky maps. The second, far more thrilling possibility is that this alignment is a real physical effect. It could be an imprint from the era before cosmic inflation, a fossil from a time when the universe's structure was first being set, leaving behind a preferred direction that inflation failed to completely erase. Some theorists suggest it might be a signature of quantum gravity, a glimpse of the granular structure of space-time itself on the largest scales. Others wonder if we are seeing the gravitational influence of an immense, unseen structure beyond our observable horizon, a supervoid or cosmic texture that is tugging on the fabric of reality and leaving a directional mark on the CMB. This anomaly is not alone. It is part of a family of strange alignments, including the curious way the quadrupole and octupole moments themselves are coordinated. If these features are real, they suggest the universe may have a privileged direction after all, a cosmic north that challenges the very idea of universal homogeneity. Could this faint axis in the sky be a clue that our local cosmic neighborhood is not so ordinary, and that the dark matter halo enveloping our galaxy might itself be shaped by this larger, invisible architecture? Deep beneath the Gran Sasso mountain in Italy, a strange rhythm pulses in the dark. For over 20 years, the DAMA/LIBRA experiment has been listening to this cosmic beat, a signal that rises and falls with the seasons. The heart of this experiment is an array of highly pure sodium iodide crystals, kept in an ultra-low radiation environment to shield them from everyday background noise. The hypothesis is elegant. Our solar system orbits the center of the Milky Way, and as it does, it moves through the vast halo of dark matter that envelops our galaxy. Think of it like driving through a gentle, invisible rain. In June, Earth's orbital motion adds to the sun's speed, so we plow into the dark matter wind head-on. In December, our motion is against the sun's direction, so we catch up to the rain from behind. This should cause the number of dark matter particle collisions, or interactions, inside the crystals to peak every June and hit a minimum every December. This is exactly the annual modulation that the DAMA collaboration claims to see. The signal is statistically robust, a clear, repeating wave in their data that has persisted for multiple cycles. The controversy, however, is just as persistent. Other immensely sensitive experiments like Xenon and Lux, which use liquid xenon as their target instead of sodium iodide, have searched for the same signal and found nothing. They see no sign of the yearly modulation. This stark contradiction has created one of the most enduring puzzles in modern physics. So who is right? The answer may lie in the details of the detection itself. Perhaps dark matter interacts with sodium and iodine nuclei in a way that is fundamentally different from how it interacts with xenon. Some theorists propose models where dark matter is not a single, simple particle, but part of a complex dark sector with its own forces. In these scenarios, the interactions could be inelastic, meaning the dark matter particle gets excited into a higher energy state when it hits a nucleus, and this effect could be more pronounced in the specific materials used by DAMA. Other possibilities are more mundane, but no less critical to investigate. Could the annual modulation be caused by seasonal variations in the experiment's environment? Changes in temperature, humidity, or even the flux of cosmic muons deep underground could, in theory, mimic the signal. The DAMA team has rigorously investigated these potential systematics and maintains that none can explain their data. The scientific community, however, remains divided, treating the result with a mixture of fascination and deep skepticism. The resolution likely awaits the next generation of detectors. Experiments like SABRE, which plans to use identical sodium iodide crystals but with even more stringent controls and twin detectors in both the northern and southern hemispheres, are designed to directly test DAMA claim. If they see the same modulation, it would be a monumental discovery. If they do not, the DAMA signal will likely be relegated to a cautionary tale about unknown backgrounds. This decades-long standoff is more than just a technical debate. It forces us to ask if we are looking for dark matter in the right way, with the right tools. Could the universe's most dominant form of matter be so elusive and strange that it reveals itself only under very specific and very rare conditions? As we search for answers in the quiet pulse of an underground crystal, we are reminded that some of the universe's greatest secrets are not shouted, but whispered in a language we are still learning to understand. And if the particles of dark matter remain so stubbornly hidden, what other ghostly messengers like the enigmatic neutrino might be carrying tales we have only just begun to decipher. Deep beneath the ice of the South Pole, sensors are waiting for a ghost to whisper its name. Neutrinos are the most elusive of all known particles, cosmic phantoms that can pass through light years of lead without a single interaction. We know they have mass, but we do not know how that mass is arranged, a puzzle known as the neutrino mass hierarchy. Think of the three known types of neutrinos, electron, muon, and tau, as a set of triplets. We know their relative weight differences, but we do not know which one is actually the heaviest. Is the order normal, with the electron neutrino as the lightest, or is it inverted, a complete flip where the electron neutrino is the heaviest of the three? This is not just a matter of cosmic bookkeeping. The answer dictates how neutrinos change flavor as they travel, a quantum ballet called oscillation, and it holds profound implications for why our universe is made of matter at all. Experiments around the world are closing in on this mystery by watching neutrinos transform. In the N-of-A experiment, a powerful beam of muon neutrinos is fired from Fermilab in Illinois to a distant detector in Minnesota. By counting how many arrive as electron neutrinos after their 500-mile journey, physicists can probe the subtle interference patterns that reveal the mass ordering. Meanwhile, the upcoming Juno experiment in China will take a different approach, using an immense sphere of liquid scintillator to capture the delicate dance of neutrinos produced by nuclear reactors with unparalleled precision. They are measuring the tiny splittings in mass, the energy gaps between the triplets, to see which map fits the data. Even natural sources, like the constant rain of atmospheric neutrinos created when cosmic rays strike our air, are being meticulously analyzed for clues. The data so far is tantalizingly ambiguous, with some results hinting at a normal hierarchy and others leaning toward an inverted one. This fundamental uncertainty ripples out from the particle physics lab to the grand stage of cosmology. The true mass hierarchy is a critical input for theories of leptogenesis, a process where heavy, early universe neutrinos could have decayed asymmetrically, creating the overwhelming dominance of matter over antimatter we see today. If neutrinos are their own antiparticles, a hypothetical known as Majorana particles, this entire cosmic story becomes elegantly possible. Resolving the hierarchy is the key that could unlock the door to understanding our own existence, revealing why there is something rather than nothing. Could the answer to this ghostly mass puzzle also help explain the origin of the most energetic particles in the universe, the cosmic rays that have baffled scientists for over a century? The universe has a built-in speed limit for the most powerful particles, a cosmic border patrol that should stop them at the gate. This is the GZK Cutoff, a theoretical barrier named for physicists Greisen, Zatsepin, and Kuzmin. Their calculations revealed a fundamental roadblock. A proton traveling across the universe with unimaginable energy should not be able to journey very far. It is constantly bumping into the faint, cold photons of the cosmic microwave background, the leftover glow from the Big Bang. For an ultra-high-energy proton, these harmless background photons are transformed into a wall of high-energy radiation. Each collision saps the proton's energy, like a marathon runner constantly tripping over invisible hurdles. Over a distance of a few 100 million light-years, even the most energetic proton should be slowed to a crawl, drained of its power long before it could ever reach our planet. Yet, against all odds, we keep catching these cosmic sprinters. Observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah have repeatedly detected particles with energies far above this predicted cutoff. These are not just slight exceedances, they are clear, brazen violations of a well-established physical law. So how are they getting through? One possibility is that their sources are incredibly close by, within our local cosmic neighborhood, so they do not have enough time to lose their energy on the journey. But when we trace the paths of these rule-breaking particles back to their origin, we often find they point to vast, empty regions of space, cosmic voids where no known celestial powerhouse exists. It is as if a cannon is firing from the center of an empty desert. This forces us to consider a much more radical explanation. Perhaps our understanding of how particles interact at these extreme energies is fundamentally flawed. The GZK cutoff relies on the precise probability or cross-section of a proton colliding with a background photon. What if that probability is not what we think it is? Could new, unknown particles be involved in the interaction, changing the equation entirely? Some theorists even suggest this could be a hint that Lorentz invariance, a cornerstone of Einstein's special relativity, begins to break down at these incredible energies. The very symmetry that ensures the laws of physics are the same for all observers might be showing its first tiny cracks. Each of these ultra-high-energy cosmic rays is therefore a direct probe into realms of physics we can never recreate on Earth. They are testing the fabric of space-time itself at energies 1,000,000 times greater than our most powerful particle colliders. Could their survival be evidence of exotic particles, like super-heavy dark matter decaying in the void? Or are we witnessing the first faint signals of a theory of quantum gravity, where the smooth continuum of spacetime becomes a frothing, granular sea? The silent reign of these impossibly energetic particles challenges not just a single calculation, but the very framework we use to describe reality at its most extreme. And if the void is not empty but filled with a sea of particles defying our expectations, what other secrets might be hidden within the nature of nothingness itself? Even the quietest room in the universe is alive with a faint, persistent crackle. In the deepest vacuum where every atom of matter has been removed, a subtle force remains. This is the Casimir Effect, a phenomenon where two uncharged, perfectly smooth metal plates, placed incredibly close together in a void, will spontaneously pull toward each other. They are drawn by an invisible hand, a force generated by the nothingness itself. The discovery of this effect confirmed a strange prediction of quantum mechanics. Empty space is not truly empty. It is a seething, bubbling sea of virtual particles, constantly flickering in and out of existence. These are quantum fluctuations, borrowing energy from the vacuum for fleeting moments before vanishing back into the void. Think of it like a calm pond on a microscopic level, where tiny pairs of bubbles spontaneously form and pop all across its surface. Now place two floating corks very close together on that pond. The bubbles forming in the narrow gap between them are limited because only certain wavelengths can fit, but outside the corks, bubbles of all sizes can form. The pressure from the greater number of bubbles pushing on the outer sides forces the corks together. This is the essence of the Casimir force, a tangible push from the activity of the quantum vacuum. We can measure this force directly in laboratories, and it is not just a theoretical curiosity. It has real-world consequences in the design of microscopic machines, where at nanometer scales, this ghostly pressure can cause tiny moving parts to stutter and stick together. Yet for all its practical intrigue, the Casimir effect points to a cosmological catastrophe. If we can measure the energy of these quantum fluctuations in a lab, we should be able to calculate the total vacuum energy they produce. When physicists do this calculation using quantum field theory, the number they get is monstrous. It suggests that the energy of empty space should be about 120 orders of magnitude stronger than what we observe it to be through the gentle push of dark energy. This is not a small error. It is the single worst prediction in the entire history of science. This chasm between prediction and reality is the cosmological constant problem. How can the vacuum energy we measure locally be so unimaginably different from the dark energy that drives the cosmos? The implications are staggering. If the quantum calculation were correct, the repulsive force of this vacuum energy would have been so immense that it would have ripped apart every atom, star, and galaxy before any of them could even form. Our universe as we know it would not exist. This glaring contradiction means our two most successful theories, quantum mechanics and general relativity, are giving us two completely different answers for the energy of empty space. One tells us the void is a roaring fire, the other that it is a gentle breeze. Both cannot be correct. Resolving this conflict is not just about fixing a number. It is the central hurdle to uniting these two pillars of physics into a single theory of quantum gravity. The answer likely lies in a deeper understanding, one where these wild quantum fluctuations are somehow cancelled out, or where our concept of the vacuum is fundamentally incomplete. Could the solution to this, the greatest numerical mismatch in all of physics, be found in the final, ultimate boundary of our universe, the cosmic horizon? Even the most voracious cosmic predator might not be able to keep a secret. When a star, a planet, or any other piece of the universe falls into a black hole, it carries with it a vast amount of quantum information, the precise details of its particles' identities, positions, and states. According to the bedrock principles of quantum mechanics, this information can never be truly destroyed. It can be scrambled and transformed, but it must, in principle, be recoverable. This is the law of quantum unitarity, a fundamental tenet of reality. Yet, general relativity, our theory of gravity, paints a different picture. It describes a black hole's event horizon as a point of no return, a one-way membrane that leads to a singularity where all known laws of physics break down. Anything that crosses this boundary is lost to the universe forever, its information erased from existence. This direct conflict is the black hole information paradox, a problem that has haunted theoretical physics for half a century. The crisis was sharpened by Stephen Hawking's stunning discovery of Hawking radiation. He realized that due to quantum effects near the event horizon, black holes are not entirely black. They slowly leak a faint thermal glow of radiation, and in the process lose mass and eventually evaporate completely. The radiation, however, is purely thermal, like the heat from a stove. It contains no information about what fell in, so when the black hole vanishes, what happens to all that quantum information it consumed? If it is truly gone, then a fundamental law of the universe has been broken. This paradox forces us to choose between our two most successful theories, suggesting that at least one of them must be profoundly wrong. To solve this, physicists have proposed some truly mind-bending ideas. The holographic principle, championed by thinkers like Leonard Susskind, suggests that all the information that falls into a black hole is not lost inside its volume, but is instead encoded on a two-dimensional surface at its event horizon, like a cosmic fingerprint. When the black hole evaporates, this information is slowly and chaotically released back into the universe through subtle correlations in the Hawking radiation. An even more violent proposal is the firewall hypothesis. It argues that to preserve information, the event horizon cannot be the smooth, placid gateway general relativity describes. Instead, it must be a searing wall of high-energy particles that instantly incinerates anything crossing it, preventing information from ever entering the forbidden zone in the first place. But this solution creates its own problems, violating Einstein's principle of equivalence, which states that an observer falling into a black hole should notice nothing special at the horizon. Recent detections of gravitational waves from merging black holes provide our first experimental data. By carefully analyzing the ringdown, the final vibrations of the newly formed black hole, scientists hope to find subtle deviations from Einstein's predictions that could hint at new physics near the horizon. Does the information escape, or is it forever trapped? Resolving this paradox is widely seen as the essential stepping stone to a final theory of quantum gravity, a framework that would unite the large and the small into a single, coherent picture of reality. The fate of information may ultimately determine the fate of our most cherished physical laws, forcing us to ask if spacetime itself is the most fundamental layer of the cosmos, or merely an emergent illusion. The orbit of Mercury was the first tiny crack in Newton's perfect clockwork universe. For centuries, astronomers tracked its path, noticing a stubborn discrepancy. The point of its closest approach to the Sun, its perihelion, was inching forward slightly faster than Newton's laws of gravity could explain. This minuscule drift was a profound mystery, a flaw in the celestial machinery that could not be ignored. It was a ghost in the machine, a whisper that something was missing. That whisper became a shout with the Michelson-Morley experiment, an attempt to measure the ether wind. Their result was a stunning null, a profound silence where a signal was expected. There was no ether, no absolute frame of rest. This failure was in fact a monumental success, clearing the way for a new understanding of space and time. These anomalies were not dead ends, they were signposts. The ultraviolet catastrophe presented another glaring inconsistency. Classical physics predicted that a hot object should radiate infinite energy at ultraviolet wavelengths, a result so absurd it was called a catastrophe. To solve it, Max Planck was forced to propose a radical idea that energy is quantized, coming in tiny, discrete packets. This desperate fix to explain the glow of a hot object became the foundation of quantum mechanics. Each of these historical moments shares a common thread. A precise measurement reveals a stubborn inconsistency with the established theory. The initial reaction is often to question the measurement, to search for a hidden error. But when the anomaly persists, it demands theoretical courage, a willingness to tear down the old edifice and build something new. The discovery of the cosmic microwave background radiation is a perfect example. Arno Penzias and Robert Wilson were not looking for the echo of the Big Bang. They were troubleshooting a persistent, annoying hiss in their radio antenna, a noise they could not eliminate. That noise, that anomaly, became the most important evidence for the hot beginning of our universe, earning them a Nobel Prize. This pattern tells us something vital about the nature of scientific progress. Our greatest leaps forward do not come from confirming what we already know. They come from the puzzles we cannot solve, the data points that refuse to fit. The 22 cosmic anomalies we are exploring today are not signs that science is broken. They are the very engine of its revolution. They are the Mercury perihelion processions of our time, the ultraviolet catastrophes waiting for their Planck. They remind us that our current models, however successful, are incomplete. The universe is always more imaginative, more strange, and more wonderful than our best theories. These inconsistencies are not obstacles, they are the most exciting opportunities we have. These 22 cosmic anomalies are not failures of our understanding, but its very frontier. Each one, from the ghostly push of dark energy to the information-eating paradox of black holes, represents a crack in the foundation of modern physics. A crack through which we can glimpse a deeper reality. The universe is not broken, it is simply more complex, more subtle, and more astonishing than our current textbooks can describe. These puzzles are not dead ends, they are invitations, an invitation to question, to explore, and to discover. They remind us that every time we think we have the cosmos figured out, it presents us with a new riddle, a fresh challenge to our assumptions. Unlocking these secrets will require our most powerful telescopes peering into the deepest void, our most sensitive detectors listening for the faintest whisper from the dark, and our most brilliant minds daring to imagine the unimaginable. It is a journey that demands continued observation, relentless experimentation, and fearless theoretical innovation. As Carl Sagan so beautifully put it, somewhere, something incredible is waiting to be known. That incredible something is hidden within these 22 cosmic clues. Which of these mysteries captures your imagination the most? Is it the silent endurance of ultra-diffuse galaxies, the impossible power of fast radio bursts, or the haunting whisper of the Flyby anomaly? Let us know your thoughts in the comments below, and subscribe to keep exploring the universe's greatest secrets with us.